So today I'm going to talk about the use of data in football. I know that football can be a bit of a touchy subject today. Um, I'm French, so believe me, the pain is still there for me as well. Just to quickly introduce myself, my name is Yannis Moudere. I graduated last year as an engineer in data science and data engineering. And during my last year of studies, I was part-time working as a data scientist for Greg, which is an AI solution for cycling. And then I did an internship at Permaculture, which used to be a Serie B club, so Italian second division. Now it is a Serie A club, and I work as a full-time data scientist there. So just to give you a short overview of how it's going to happen, I'm going to first present the data that we have and what we want to infer from it, then how big the volume is and how tricky it can be, and finally how we handle it. And to conclude, I'm going to show you some examples of what we do in real life. So what kind of data do we have in football? We have two types of data for games. Today my presentation will be focused on game analysis. And these data comes from different providers that you can see here. So first we have event data that answers the question, what happens during the game? And tracking data answers, where is everyone? So this is an example of event data. So it's simply a table with one row per event in the game. And an event can either be a pass, a carry, an interception, a tackle, a goal, etc. And for all of these events, we have some columns that we call qualifiers. So some temporal qualifiers, the period, the minute, the second. Also the player and the team, the coordinates, the outcome, which is 1 if the event is a success, 0 if it's a failure. And as you can see, all these events are related to what happens around the ball. But as you may know, football is not only about what happens around the ball. Context is very important in football. And so the question is, how do we add context to these events? So context can be provided by analyzing off-ball movements, and that's where tracking data comes into play. Tracking data is simply the position of the players continuously during the game and the ball. And from the position, we can derive the velocity that you can see here with the arrows. And in terms of volume, this is 25 frames per second, which equals to 150K frames per game and 3.5 million coordinates. And this is what we need to analyze off-ball movements. So now I'm going to go through some models that we infer from tracking data, and then I'm going to show you how we use it. So the first model is pitch control. It has been defined by Javier Fernandez in his thesis, and it's basically it defines the influence of a player based on its initial position and velocity, and it's the probability that the player is reaching any area in the pitch based on its initial position and velocity. And if we aggregate this at team level, we get something quite nice that we call pitch control. And this is what team controls what area continuously during the game. And this can either be analyzed at team level or at individual level. So we define the individual pitch control as the proportion of the total influence that is created by this player. So here you can see that the left fullback has much more control than any other player in the left wing. So we can quantify his freedom. Another model is the pass options. So this, for a given frame, a given time frame in the game, we can compute several maps that contain complementary information. So in the first one, for example, we have the pass selection probability. So for this situation, the ball is here in the feet of the goalkeeper. And in the first map, we estimate what the probability that he chooses any area in the field to make a pass. And we can see that it's very likely that he chooses a short pass to his defenders. The second one is the pass success probability. So if he chooses any area, what is the probability that the pass is a success? And again, it's more likely to be a success if it's a short pass. And the third one is the pass expected value. So it quantifies the dangerousness of any area in the field based on the current position of the players. And these models are very interesting in football. They can be used separately or combined to define what we call the expected possession value. And to explain a little bit, the expected possession value is an estimate of which team will score the next goal based on the current dynamics of the game. So here you can see the timeline of the expected possession value. It's between -1 and 1, and it's positive when the team is more likely to score, and it's negative when it's more likely to concede a goal. So here, for example, you see that when Barcelona's opponents intercept the ball, Barcelona, the expected possession value gets negative because they are most likely to concede a goal. And then they take back the possession of the ball, and it gets higher and higher, and it reaches its peak when they are heading to the box. And then it goes down when there are pressure on them. So this quantifies the dangerousness of any action during the game, and this is very interesting in football. The third model is the pressure. So based on the position of every player and their velocity, we estimate the pressure that the player in possession of the ball is undergoing. So here you can see that the blue team has possession of the ball, and for each opponent we see how much they pressure the player in possession. So all these models are models that we use in football, and now I'm going to show you what we want to do with them. So let's go back to event data. The objective of my presentation is to show you how to enhance events. And by enhancing, we mean adding context. And context is simply a column. So for each event, we can add the pressure that the player is undergoing at the moment of the event. So here you can see that here, Papetti, Brescia's player, missed a pass that led to an interception and then a goal. And if we add the information of the pressure, we can say, okay, he missed the pass, but because he had a lot of pressure on him. Another thing that we can add is the expected possession value at the start and at the end of each event. And this helps us quantify how much each event contributed towards winning the game or losing the game. So here with his interception, Denis Mann, the player from Parma, generated an XPV of 0.65, and then he concluded with a goal. So this is just some examples of columns that are tracking based and that we can add to event data, but there are actually many more. And why is it not so easy to add these columns? First, because these metrics are computationally expensive. We have a lot of frames and a lot of pixels in the pitch, 6,500 cells, and not all operations are parallelizable. Moreover, we also do convolutional inferences for the pass options maps, which require very heavy calculations. So this leads us to the first problem, which is how to efficiently compute all the required features for a game. In terms of volume, one game is 250 megabytes of tracking data. And to process the game, we need 8 gigabytes of RAM for 150 seconds. Knowing that one season of one competition is 380 games, this leads us to 95 gigabytes of storage. And to process everything, we need 500K gigabyte seconds of memory. So this represents either a lot of RAM or a lot of time to process everything. So yeah, how to deal with huge amounts of data every time a new feature is added. Because every time a new feature is added, we need to process again all games. And this is illustrated here. We have here the volume to process, and it's very high when we want to process every game. But also we have a continuous flow of games arriving daily because football never stops. And this leads us to a problem that we have to set the computational availability. If we set it to the maximum volume that we have to process, we will be able to process every game, no matter when, but we'll waste a lot of resources because it means that we have to maintain this amount of resources every time, and this means a lot of money. So another possibility is to set it lower, but this means that we'll need extra time to process the remaining games when we have a huge load. And knowing that we'll have new games arriving daily, it's going to be accumulated delay every day. So this leads us to the third problem, how to scale the architecture on a cost-effective way. So now we can dive in the solution, and the solution that we propose can be used also in other sports or on other industries where you have a lot of data stored in your database, and you also have a flow of data arriving daily. So we have one machine which is always on, and that pulls the different providers' APIs. It passes the game and upload them in the data lake. And then once the event data and tracking data are in the data lake, we can process them asynchronously. So decoupling the downloader from the processor allows us to scale the processing part. And how do we want to scale? We have two options. We can either scale vertically or horizontally. Vertical scaling means increase the size of the machine accordingly to the volume that you want to process. So you just keep one machine, which means that you don't have synchronization to do between several machines, but it is limited by the physical resources that your machine can handle. And the fault tolerance is not optimal because it's a single source of failure, meaning that if your machine breaks, you don't have any backup. Another possibility is to scale horizontally, which means increasing the number of machines accordingly to the games you need to process. And so this requires synchronization between all your workers, but the scaling is unlimited, meaning that you can turn on a new machine every time. The only limit is the price that you can pay for it. And the fault tolerance is improved because if you lose a machine, well, you have the other workers to make the job. And that's why we chose to go with horizontal scaling. So we can have a first look at the first bricks of our architecture. I'm showing AWS icons because that's what we use at Permaculture, but other cloud providers have similar solutions. So you can use other cloud providers too. And so we have the downloader, which is simply a virtual machine and writes on the bucket that symbolizes the data lake, and it scales the workers accordingly to the load. And having the downloader separated from the processors, we need a system that manages the scaling of the workers. And for this system, we needed to verify some constraints. The first one is the load balancing. We want to distribute games equally across all machines. We also want the processing to be asynchronous, meaning that we don't want to wait for an immediate response before processing other games. And we want the system to be fault tolerant. So if a machine crashes, we need to be able to back up. And that's where the message queue comes into play. So a message queue is simply a system in which you write files. So one file for us is a game that we need to process, and we'll have workers fetching from this queue. So the downloader writes the file that need to be processed, and the workers just fetch the message queue. And so this allows us to balance the load, and to process everything asynchronously. In terms of fault tolerance, we need the message to be processed at least once, and this is ensured by the fact that the message stays in the queue until it is fully processed. Two workers cannot process the same file at the same time, and for that we have what we call a visibility timeout, meaning that when a message is consumed for the queue, it's not visible anymore for other workers the time that we process it. So they can't fetch the same game. And also file triggering errors need to be set aside and analyzed. This is made possible by what is called a dead letter queue. It's simply another queue that's going to contain every message that triggered an error, so that you can manually fetch in this queue and see what went wrong, and then put back the file in the queue when it's fixed. So we can update our architecture with the queue here, AWS SQS. And depending on the number of messages in the queue, we scale the number of workers, meaning that if we have a lot of messages to process, we want to have many workers on. And if we have no message in the queue, we don't want any virtual machine running. So this leads to the question to how many workers do we need to scale the architecture? The good thing with our solution is that you can set the maximum time that you can wait to have a game processed, no matter the number of games in the queue. So this is made possible by simple rule of three. We need 150 seconds to process a game, and if we set a maximum time of 10 hours, it means that every machine can process 240 games. And this way we are sure that in 10 hours the matches will have been processed. So to illustrate that, we can go back to our volume to process, and every time the number of games that we need to process is lower than 240, we just have one machine on. If it's between 240 and 480, we have two machines on, and so on and so forth. So this way, we are sure to have the right amount of workers on, and to only pay for that. So this is a discrete way of seeing things, but in practice, we adapt it continuously, meaning that we have a monitoring service that computes the message to worker ratio continuously. And if we are overloaded, it turns on a new machine. If we are underloaded, it turns off a machine. And at the end, you can see that when we have no game to process, you don't have any machine on, meaning that you don't pay anything. So here we can add our monitoring service, which is AWS CloudWatch. and it computes this message to worker ratio continuously and accordingly scale the number of workers. So now we can focus on our machines. So cloud providers have two distinct offers for machines. They can either be on-demand or spot. Understand that these are the same machines, it's just two different offers. In both cases, you can scale your capacity instantly, meaning that you can increase it or lower it whenever you want. But the main difference lays in the price, because for on-demand, you have a fixed price per second, and you pay for how long the machine was on. It's different for spot instances, because spot instances are your cloud provider's unused capacity, and you have market price that fluctuates over time depending on supply and demand. And if you have to bid a price, if your bidding price is lower than the market price, you don't have any machine. If it's higher than the market price, you get a machine. In terms of reliability, on-demand instances are fully reliable, and it's not the case for spot instances, meaning that they can be turned off at any time, independently of your will. So you got to be prepared for it if you want to use them. And the availability is guaranteed for on-demand. It's not for spot instances, meaning that if your bidding price is too low, you don't have any machine for you. So we chose to go with spot instances because it's much cheaper. And as you may know, we have very few money in the football industry. But we have the reliability and the availability problem that are actually not constraining for us, because the reliability is made sure by the message queue. Because if you have a machine that breaks and it was processing a game, the game will not be deleted from the message queue. So it will stay in the message queue and just be fetched later by another worker. And for the availability, well, if your bidding price is too low, you just have to increase it a little bit. So you'll pay a bit more, but at least you'll have your games processed. And in terms of prices, spot instances are a lot cheaper. So we make up to 90% savings. So we can just update our architecture with spot instances. And the final step of our solution is teaching the machines what we want them to do when they are on. And for that, we have something quite convenient that is called user data. And it is a line of commands that the machine is going to run in the terminal every time it's turned on. So we just give it a list of commands. We create a virtual environment. We do the pip install to install the dependencies. We do the git pull to get the code from the private Git repository. And finally, we run a Python script that fetches a message from the queue, get event and tracking data in the data lake, compute the metrics, and then upload the new columns in the data lake. And this process repeats until the machine is turned off. The only thing that we have to do is to add messages to the queue and to update our Git repository to have the latest version and the latest features that we want to compute. So yeah, we arrive at the final architecture with AWS code commit to to store our code, and the machine just read and write the data lake. So now I'm going to show you how it works in real life, and I'm going to show you some nice dashboards that we use at the club. So we actually have ETL services, so extract, transform, and load services that are going to fetch the non-tabular data that we created in the data lake, and they're going to put it to Redshift in the data warehouse, which is similar to a database. And we have Tableau directly extracting from our data warehouse to produce the dashboards for the scouts, for the staff, etc. And so our pipeline is continuous integration, continuous development. We can just build the features we want to build, test them locally, push them, and then we have some tests to make sure that it doesn't break our process. And finally, the code is deployed. And when we want to process a game, we just have to add it to the queue, and we know that all the process is automatic, and it requires no intervention from outside. In terms of performance, we compared it with a serverless solution with one machine constantly on, and with the same solution but with on-demand instances. So we have to pay thousands of dollars for each game. So if you have a database with 10,000 games, it's $10, which I think is affordable for a professional football team. And we also have the load of games arriving daily. So this represents a fixed price of $1.5. So in total, what you will have to pay is $10 every time you want to process again all games, if we have 10,000 games in your database, and $1.5 monthly. So yeah, to compare it with other solutions, it's longer than serverless because you can scale a lot with serverless, but it's much cheaper. And compared to an always-on virtual machine, is shorter, much shorter, because we have a lot of workers doing the job when we have a lot of games to process. And it's cheaper because, well, when we don't have anything to process, we don't pay anything. And finally, the dashboards, the most exciting part. So in the club, we use data for three different purposes. The first one is scouting. So here you can see some players that are filtered by position. I think they are all wingers. And yeah, we selected some metrics that are these metrics. We use them for wingers. We have other metrics for other positions. But yeah, you can compare it between players. And if you select a player, I picked one randomly. I think you guys like him. Yeah, so we have some personal data coming from different sources, and also some performance data that we compute with our event and tracking data. And we can, and so these dashboards are in the hands of the scouts that can explore all the players, compare them, and they can also dive deeper in the analysis. So this is for the same player, the pass map, showing every progressive pass. And we also have a shot map here, with the positions from where the player shoots the most, and a shot map, a goal map, sorry, showing how accurate he is. And yeah, this is a tool that our scouts enjoy. The second purpose of the data that we make available is for pre-game analysis. So this is used by the staff, the coach himself, and the match analysts. And yeah, so our next game is the first game of the season against Palermo in Coppa Italia. And yeah, the match analyst can compare Palermo situated in the league for tons of metrics, and they can also have an individual report for each player, showing different metrics, showing how they rank in the league with the color. So it's already highlighted, and here you can see also all the passes for this team that you can then filter on player or match to analyze it more into details. And the third purpose is post-game analysis. So after each game, our coach and our staff receive a report of what happened during the game, and this is quite detailed too. So this is a pass map, and this allows to say if the player performed well under pressure, because it's based on the pressure that he was undergoing at the moment of the pass. And so you can see that here players with the green arrow performed well under pressure during this game, and the other didn't. Yeah, you can also visualize line-breaking passes from where to where, which line did they break, etc., etc. And finally, an individual, the individual characteristics of the game. So yeah, the staff can play with all this data, and they have some insights from it. So that's all for me. Thank you very much for your listening. And I also would like to thank the team at Parma, because this is a teamwork, and thank you for the organization as well.
Any questions? Yes. Very cool talk, by the way. Thanks. In one of your very first slides, you showed, I think, the danger heat map, that little GIF that kind of showed like, yeah, bunch of slides. But what I was like, what kind of techniques, like from a machine learning perspective, could you maybe shed some light on how that is estimated? It's like,
yeah, of course.
There's a kernel density estimator in scikit-learn, but you might be doing something more fancy than that. It's an amazing slide game.
This?
Yeah. Yes, yes.
Okay. Yeah, so this is computed with convolutional neural networks. So basically how it works, we have every pass that we have to merge with tracking data, because in event data you just have the pass and the minute and second, but we need to be very precise to have the exact frame where the player made the pass. And then how it works is you have some features like just the positions, the velocities, some other features like the lines, the attacking midfield, defensive line, some stuff like that. And you train the model to be able to output the selection. And same for pass success probability. Here the output is 0 if it's a missed pass, and 1 if it's a success. And to produce, so you have a network which is outputting a map, and to train it, you just look at the output of the model where the pass was aimed. So to train the model, we don't have a full map as output to compute the loss. You can just look at the loss at the particular point where the player made the pass. And if you have a lot of passes, it still can be trained.
Cool. Yeah. Thanks. Makes sense.
Thanks a lot for the talk. You just mentioned that it's very important to have the exact moment from when the pass was happening or when the shot was happening. I happen to know that like event data and tracking data most often do not perfectly align with the daytimes and stuff. What kind of method do you use for this precise synchronization of the event and tracking data?
Okay. So yeah, we have data coming from different providers, so we have to merge them ourselves. And to merge them, well, we already have the minute and the second, so the wide of range, the range of motion is not this long, this big, because yeah, you have like a 2 seconds, a 2 seconds range, and you have to find the exact frame in this range. So basically, you can look at the distance between the player and the ball. You can look at the velocity of the ball, knowing that when the velocity in the direction of the pass is higher than some threshold, it means that's very likely that's the moment when the pass was made.
So you basically have a cost function within a specific time period for each individual event.
Yeah.
Okay. Thank you.
Yeah, thanks. It was very interesting. I was wondering, where do you get the data from players from other clubs? Because I can imagine that PSV does not want you guys to know how all the data about Noah Lang, for example.
Yeah, so the data does not come from PSV itself. We have data providers like Skill Corner, Opta, that process the data. And for example, for tracking data, it's based on the broadcast video of the game. So you don't need to work for PSV to have this data. It's just contracts between you and the data provider.
Okay, so it's just like match data then. Right?
Yeah, yeah.
So only things that were shown
We
on
only
TV.
have match data, yeah.
Okay. Nice. All right. Thank you.
Yeah, thank you very much. One more comment about the complexity of merging event data and tracking data. You just mentioned one solution, but what were other problems and solutions you found along the way?
Yeah. So actually, it was a bit tricky. At the beginning, I thought it was possible to be made in a few days, but it took more than that. Yeah, just for the merging part, not for everything, but just for the merging. And yeah, sometimes, so I mentioned the velocity towards the direction of the pass. Sometimes you just have the player running in that direction before making the pass. So yeah, it's a bit of combining this velocity, also the distance between the player that makes the pass to the ball, because if he makes a pass, it means that in a few milliseconds, the ball will be further away from him. So yeah, it's like combining different criteria.
All right, one last question.
Thanks. Hey, Yannis. Yeah, really nice presentation.
Thank you.
I think everyone here enjoyed it. Yeah, so interesting to see what the data maturity is like at Parma Calcio. And it's also maybe assume that there's some user adoption in the end product that you deliver. These dashboards are being used. So my question is a bit about vision. What is the next step at Parma? Is there maybe a use case for live streaming data during matches? Are you looking at a foundational model to implement? A bit of what's next,
Yeah.
actually.
So actually, I joined the club as an intern 10 months ago, and before that, the club had never worked on tracking data. So we are still learning on tracking data and see what we can infer from it. It's still a transition phase where we are integrating some stuff that I showed here and other stuff. We have some work to do for the analysts to facilitate their work. And I think, the next step will be focused on tracking data because there are much more to do in this direction,
Thank you, Yannis. Another round of applause, please.
Thank you.